Hello, in this video we will be looking at stationary points for functions of two variables. This here is just a recap of what you would have already seen with respect to a function of a single variable, where the stationary points for a function f of x is found by finding the gradient, the derivative with respect to x, setting that equal to 0, and solving for x. And there are three types of stationary points for a function of a single variable. They are minimum points, maximum points, and inflection points. So this here is just an example of that. I am not going to go into this into too much detail. But here on the left, we see we have a minimum point. The point in the center is an inflection point, and the point on the right is a maximum point. Okay, so when we switch to looking at a function of two variables now, we will have something similar happening, except we will no longer have inflection points. So we will still have minimum and maximum points, but the inflection points, we'll actually call them something different. We'll call them saddle points. So for a function f of xy, or a function of two variables, the stationary points occur when the partial derivatives, the first partial derivatives, are 0. So before we would have differentiated with respect to x, set it equal to 0 and solve. We do something similar, but because we have two variables here, we have to differentiate with respect to x, set that equal to 0, and also we could take the function and differentiate with respect to y and set that equal to 0. So what we will end up with is two simultaneous equations that we need to solve. Right, solving both of these equations will give us our stationary points, and we'll talk about the classification in a little bit. This here is just a graphical representation to show you what these points look like in 3 dimensions for a function of two variables. So a minimum point looks something like this on the left, a maximum point in the middle, and then our saddle point, which I mentioned before, looks like what we see on the right here. Now with the saddle point, depending on your point of view, suppose I was looking at this from this surface from this direction, then you would see that it could be curving like a minimum point, whereas if I rotate it, it look like a maximum point. Whereas in fact, what is happening is this is neither. This is it from one direction it looks like one type of point, but from another direction it looks like a different type of point. So we call that a saddle point, mainly because if you look at it, it kind of looks like a saddle. Right, so this is just talking about local and global points. We're not going to go too much into this, right? So we are finding minimum and maximum points. Those will be local minimum and local maximum points. And also saddle points, just saddle points in general. Okay, so let's go straight into this. So there are two things we'll need to do with respect to stationary points. One is to find them, and then the second one is to classify them. Right, as I mentioned before, if you want to find stationary points, we find the first partial derivatives, the two of them, and then we set them equal to 0 and we solve for x and y. So we'll have two simultaneous equations which we will be solving for x and y, and that will give us our stationary points. Once we have our points, then we need to classify them as either a minimum, a maximum, or a saddle point. Now, to classify stationary points for a function of two variables, we need to find the second partial derivatives. So the second partial derivative with respect to x, second partial derivative with respect to y, and the second partial derivative with respect to x and y. Now, because these functions are continuous, it does not matter whether this one is the derivative with respect to x then y, or y then x. They will both be the same value. Right, once we have our second partial derivatives, then we need to substitute the values that we found for each point, for each of these stationary points separately. Suppose I had found 2 points, and I would take the first point, substitute x and y into those, and then calculate this expression. And depending on the value of this expression, that will tell me what my point is. Right, so what we do is we take the partial derivative, the second partial derivatives for with respect to x and y, we multiply those and then subtract the second partial derivative with respect to xy squared. Right? This one has to be squared. Right, so I usually use something like this table here to tell me what the classification would be. So here in the first column we have the value that we found from this expression for our given point. So we have three possibilities. Either it's positive, it's negative, or it's zero. Now I'm actually going to start from the bottom of the table and go up because it's easier to explain that way. So if for whatever reason this value works out to be zero, then this test actually fails and you cannot draw any conclusion from that. All right, now this is not something you're going to actually encounter very often. This is a very rare scenario. And the problems that you will be looking at, it will be either one of these two things usually. So it's either going to be positive or negative. All right, but just bear in mind that if it is zero, you cannot draw any conclusion. Now, if the value that you found here from this expression with the second partial derivatives, if this was negative, then automatically you can stop and say, well, okay, this point is a saddle point. All right. Now, if it turns out to be positive instead, then we actually have two possible subcases to look at. It could either be a minimum point or it could be a maximum point. And how you determine which one it is by looking at the second partial derivative with respect to x. Right. You can also look at it with respect to y because they will give you the same conclusion. So let's say the second partial derivative with respect to x was positive, then that tells me I have a minimum point, a local minimum point. If that value was negative, then I would have a maximum point. Okay, so let's look at a couple of examples just to see how we actually do this in practice. So here we have a question. We have a function f of xy is 3xy minus x cubed minus y cubed. Okay, so we need to find and classify our minimum and maximum points. Now it says to find and classify all minimum and maximum, but if I found any saddle points, I need to indicate that as well. So what we need to do is first find the points, and that is by finding the partial derivatives, the first partial derivatives with respect to x and y. Alright, so we differentiate with respect to x, we'll get 3y minus 3x squared. Then we differentiate with respect to y, we get 3x minus 3y squared. These are our first partial derivatives. The next step is to take these and equate them to 0. Alright, and then see what happens from that. So if I take the first equation, the first expression equated to 0, I get this equation, and I could actually make y the subject of the formula, y is equal to x squared. From the second expression, when I equate that to 0, I'll get 3x is equal to 3y squared, or x is equal to y squared. Now, at this point, I like to number these equations at this point because you're going to end up with two simultaneous equations, and the actual method used to solve these equations will vary depending on the type of equations they actually are. In this particular case, right, I can't eliminate a variable by, let's say, multiplying this equation by something and then equating. I can't just equate things in this case. Sometimes you could do that. But in this case, what I could do is, well, y is equal to x squared, and here I have an x in terms of y. So I could take this equation and substitute for x into the first equation here, and then that will eliminate my x variable. All right, so when we do that, we get y is equal to, well, we have y squared, squared will be y to the power of 4. Now be careful here, don't just see y is equal to y to the power of 4 and go and divide by y, because if you do that, you lose a solution, right? Because if you divide by y, then what happens if y is 0? Well, you've just divided by 0, and you always want to avoid that. So the best option is to always carry everything to one side of the equation and factorize. So when I factorize, this is what I get. Now, this equation tells me that either y is equal to 0 or y is equal to 1. So we have two possible cases, y is 0 or y is 1. And then these two possible cases, I could use and find my corresponding x values. So I have two equations. I could substitute into either one of these equations and get my answer. So I could take, for example, this equation, because this has x as the substituted formula and I want to solve for x. So when y is 0, I'll get x is 0. When y is 1, I'll get x is 1. Right, so those are my 2 points. My two stationary points are, well, remember when y is 0, x is 0. So 0, comma 0 is 1 point, and then 1, comma 1 is the second point. These are my stationary points. Right, just pair up the x and y values. And then we move on to classification. So now we need to find the second partial derivatives. Now, don't go from the start and just differentiate all over again. Just take the first partial derivatives and differentiate those. So if I want a second partial derivative with respect to x, I could take this first expression here, differentiate this. That'll give me negative 6x. Then the second partial derivative with respect to y, I could take this expression, differentiated. That'll give me negative 6y. And then for the second partial derivative with respect to x and y, I could take either one and differentiate with respect to the second variable. So I could take this and differentiate with respect to y this time. That'll give me 3. Alright, so these are the expressions we get. So what we need to do is work out, remember we need to work out this expression multiplied by this one minus this one squared. So we're actually going to end up with 36xy minus 9. Alright, now once you have that expression, I didn't state it here, but once you have that expression, you substitute your x and your y values. So the first point is 0, 0. Right? So when you take x and y as 0, you'll end up with negative 9. Right? 36xy minus 9, 0 and 0, that'll give you negative 9. Which means it's a saddle point because it's negative. Now when you take 1, 1 and substitute it, you'll get 36 minus 9 gives you 27, right? And that is positive. So now you need to go and look at either one of these and see whether it's positive or negative. So substitute x is 1 into this one, that's negative 6, that is negative, which tells me it's a maximum point. Right, now how I did it here is actually a little different, so this might actually be an easier way to do it. So you put on you create a table. So the first column is a point, then you can take the second derivative with respect to x, second derivative with respect to y, second derivative with respect to x and y, and then you have in the next column you have the value that you're looking for, this expression. And in the last column you have a classification. So you put down, in each row you put down each point, so 0, 0, 1, 1, and then using these we can actually using these we can calculate each value as we go. So the fxx value, when x is 0 we get 0, when x is 1 we get negative 6. Same thing for this, 0, negative 6. Here, well, this is just 3. And then to get this value, we take this the first value multiplied by the second value and then subtract the square of this value. Alright, so then you get negative 9 here. Minus 6 times minus 6 is 36. Minus 3 squared is 27. Alright, now when it's in this table form, it's much easier because, well, the saddle point is straightforward. But for the maximum point, when you see a positive value here, then you look across here and see, well, is this negative or positive? As long as it's negative, it's going to be a maximum point. If it's positive, it's a minimum point. Alright, so it's pretty straightforward. I will look at one more example here. Well, actually, I'll just quickly go through these. So here we have our function f of xy is given by this expression. So we go through the same process. We find the first derivative with respect to x, with respect to y, and we equate them to 0. Now from the first equation, it can be a little tricky sometimes. Notice I can make y the subject of the formula. If you can ever make a variable the subject of the formula, it's always nice to do that because you might be able to substitute it later on. So in this case, I left it as 4y because I didn't want to have any fractions, but also because I could get a 4y from the second equation. Right? From this equation, I could get a 4y if I divide by 2. And because I have a 4y here is equal to this expression and a 4y here, I could equate both of these because they're the same thing. So you equate the right hand side of both of these equations because the left hand sides are equal. And that allows me to get an equation in x alone, and then I can solve that. Alright, so we end up with x is plus or minus 2. And again, remember when you take the square root, it has to be the positive, but you can either take the positive or the negative. You have to consider both. Okay, so we have the x value. The easiest equation to use to solve for y would be this equation here, the second equation. Okay, so we use our x values, both plus 2 and minus 2 and then plus 2. When x is minus 2, we get 0. When x is plus 2, we get 2. So our 2, we have two stationary points, minus 2, 0, and 2, 2. Alright, classification, same process again. We find the second partial derivatives. So we take this one, differentiate with respect to x again. That gives us this expression. Take this, differentiate with respect to y. That gives us this, well, it just gives us 8. And then we could take this and differentiate with respect to x, and that'll give us negative 4 for this. Alright, so we create our table, we write down the 2 points, and then we have, well, this value when x, this only depends on x, right? So when x is negative 2, we'll get negative 12 plus 2 is negative 10. When x is 2, we'll get 12 plus 2 is 14. And these here, well, these are nice because these are just constants. So I could just write those back. I don't need to work anything out for those. Alright, and then remember this value, you're going to take the values in the first two columns here, well, the first two values that we found, multiply them, and then subtract the square of this value. You have to be careful here because you're squaring this number. So this will go to 16. So you'll have minus 80 minus 16, that gives you minus 96. Alright, similarly work the second one out, you get plus 96. Alright, now remember when it's negative, it's a saddle point. If it's positive, you need to come to look at this value here or this value. In this case, it's positive, which means it's a minimum point. Alright, this example here is just one where it's inconclusive. I'm not going to go through this one. You can go through it yourself just to make sure you understand how to do it. Alright, this function here, just make sure you understand the working involved. But you're not going to get something like this where the test itself is inconclusive. Alright, this is another one that is, I think is a good idea to look at. So I think this is the last example here. So I'm going to skip through this a little bit. So we have the function, we differentiate, set it equal to 0. Now, when I set the first one equal to 0, notice this is in terms of x alone. Similarly, this is in terms of y alone. So what I'm actually going to end up with from the first equation is I'm going to get two values for x. Right? Now, these two values for x on their own don't allow me to solve for y. I have to solve for y from the second equation. So from the second equation, we get two values for y as well. Right, now if this was just a single value, then we could just, well, say pair the first x with the y, then the second x with the y, and that gives me 2 points. But the thing here is x could be either one of these, and y could be either one of these, and there's no restriction on which one goes with which one. And when that happens, it means you have to consider all the possible cases. So it means that this x is equal to 1 has to be paired with both y values, and this x is equal to 3 has to be paired with both y values. So that gives me 4 points this time. Alright, so we end up with 4 stationary points in this case. We proceed with the classification as before, so we find the second partial derivatives. I've listed those here. And then we create our table, put down the points, and calculate the values. Alright, so we calculate the values, then we calculate the value that we need for the classification. So the two middle ones, negative, the value is negative, so it automatically saddle points. Now, for the first one, it's positive, but this is negative, so it's going to be a maximum point. And then for the last one, positive and positive, so it's a minimum point. Alright, and there are these two links give you some additional practice problems, as well as some more worked examples. So if you do need any more practice, please use these links and make sure you understand how to do these problems, because they are actually really straightforward and they're really nice to do. Once you know, once you're comfortable with your differentiation and you're comfortable with the overall method of doing it. All right, so that's pretty much it for this video. So I will end this here.